Welcome back. Last time we talked through rockets, kind of finishing out the jet versus rockets. We went a little bit deeper into the rocket equation and different factors on the rocket. And so now it's time to kind of start talking about hypersonics in a little bit deeper framework, not too deep yet. And so I've started here with just an easy diagram of an aircraft flying through the air at a speed v. And it's got four fundamental forces acting on it. The first one's flying through the air, so there's a drag. Opposing that drag is the thrust of the engine's T. And the vehicle has some weight. Now it gets lighter as it burns off fuel, but it's got some weight that is changing again. And then based on the angle of attack, right, the angle of the aircraft going into the wind, based on the wings and the lift, it'll have some lift L. And again, the lift needed as the aircraft gets lighter will be less and less. So for the same wings at the same speed, you will actually have the aircraft able to do less of an angle into the wind. That'll be important here in a second. And so what we want to talk about is, well, what is the range of this aircraft? How far can it go? And so that range R is just the speed of the aircraft times how much time, right? How long is it flying? Well, it's not the easiest way to deduce how long it can fly because, it depends on how much fuel it's carrying and what's the rate of its fuel. Well, again, the aircraft is getting lighter as it goes, so the burn it needs on its fuel is changing. So this doesn't quite work for us. And so what we need to do is talk about a little segment given a little moment in time. So at this kind of snapshot in time, the aircraft weighs this much, is burning this much fuel. How much, little range is it getting for that little moment in time? And then we would add them all up or integrate. And so this is a little bit easier to cast because this is now just how much mass, right? I burned a little bit of fuel. And then how much, what's my fuel rate? So how much fuel, say in pounds, and then was my fuel rate pounds per second. This would give me now how much range I did in a little kind of moment in time, a little segment. And so we can then think about the thrust of the aircraft because mass flow rate is related to the thrust. And so kind of going back to the equation that thrust is actually mass flow rate ISP times gravity. We have an equation for m dot, and so I'm going to substitute that in. And so dr is the speed of the aircraft, and then 1 over m dot, and so you get ISP times gravity divided by the thrust, and then again that dm shows back up. But thrust is simply drag, right? If this aircraft is not accelerating, then thrust is equal to drag. And so I'll put that in there. But at the same time, I'm going to multiply top and bottom by lift. And so this is then V ISPG. And then you have drag on the bottom. I'm going to multiply top and bottom by lift. So I have a lift over drag. And then there's the 1 over lift. So those lifts do cancel out. And then I have dm. Now, the same sort of trick. What is the lift? Well, the lift is the weight. And the weight is the mass of the aircraft times gravity. Well, perfect. So that gravity is going to cancel out with the gravity on the top. And so in the end, you have V ISP L over D dm over that m. Perfect. And so now I can integrate this because this was the dr. And I integrate that. I'm going to get that natural log again, just like we saw in the rocket equation. And so I'm going to go ahead and skip forward to the final end. Instead of just saying final over initial, I'm getting a little low on the board here. We integrate that. You get the initial over the final. I'm going to convert that into the other form we were using. And so the initial is how much propellant I used to get up to that cruise speed. So one being takeoff weight, 1 minus lambda cruise being how much I used to get to cruise, and then 1 minus lambda total, the total packet of fuel or propellant that is carrying. Now, again, for a purely turbine-based combined cycle, that's only fuel. For rocket-based combined cycle, this would represent both the fuel and the oxidizer, so the total propellant being used. Okay, so last time in the rocket equation we talked about kind of the fuel to get to the top speed. So that's actually going to represent our lambda cruise. And so, when we're flying hypersonically, it does take a significant amount of fuel just to get up to the top speed, even time, depending how you're getting there. And so you need to bring back up, again, that rocket equation. And so you had MA is equal to thrust minus drag, but this time I'm not going to cancel the drag. Still going to ignore gravity for right now. And this is thrust 1 minus, and then it'll do kind of the same trick we were doing here with these 4 vectors. And so after you go through it, this is thrust away to the vehicle, lift to drag. Right? And so this is important because if the thrust away to your vehicle is not very big, it'll take you a long time to get up to speed. You're fighting drag the whole time you're getting up to speed. And so there's a penalty. And so this term carries forth. And so when we do that final integration, and you talk about delta V, which would be, if we're starting from rest, that's 0 to our cruise speed. This is equal to ISP G. And now you get that penalty term in front of it. So you get that 1 minus 1 over thrust to weight, lift to drag. And then you have that natural log, 1 over 1 minus, in this case, it's lambda cruise. We're trying to get up to that cruise speed. So you have this penalty term that shows up. And I'm going to draw that picture we talked about in the jet engine section, where this might be Mach number. And you had, remember you had the drag that kind of spiked at Mach 1, 2, 3, 4. And we talked about the thrust of a jet engine in a turbo-based combined cycle situation that might do something like that. And then, of course, there's the ram start again. But remember that thrust pinch. And so this penalty term, even though we sort of integrated it here and pretended like it was constant, it's not constant. And so really it's actually kind of going back up to this term, and you have to kind of integrate your way forward. But right here, right, the lift of the aircraft compared to the drag is pretty brutal. And so, this is why kind of like, if you look at a military aircraft, the standard thrust to weight might be something like 1, just to make sure you can get through the sonic bound barrier. And so, as we then want to kind of compare the two systems, so compare rocket-based combined cycle and turbine-based combined cycle, now that we kind of have a little bit of the framework, right, we'll do 2 things. And so, giving myself some room here, I'm going to put rocket-based combined cycle in green. And I want to look at a few terms. I want to look at how much it takes to get to cruise speed. We want to look at, and this is kind of percentage mass of the system. We want to also account for mass of the entire propulsion system. And then we'll look at the total stack up. Right, this is your total propellant plus engine. So we can really kind of compare the two. And so then we'll take also look at turbine-based combined cycle. And so this is the ISP curve shown in the past versus Mach number. And so what I did here is kind of overlaid a couple curves. One in red, I said, here, I'm going to give turbine-based combined cycle some credit. Maybe they're actually operating at 3,500 seconds. That's pretty, for an engine going into turbine-based combined cycle, that might actually be pretty high. But I'm going to give it credit up to about Mach 1, and then it's going to kind of follow the curve. Now, we're both chasing this blue curve. They're both chasing kind of this ram start and then operating in a ramjet mode. And so both systems are going to give credit for that blue curve. And then in the rocket-based combined cycle, kind of doing the bottom one. So about 1,000 seconds, which, some of what we've seen in Venus, when you kind of mix in the air, you're getting some good numbers like that. And then as you kind of get the ram effect and actually we're able to start that ram burner early, so we get some more thrust that's a little closer to ramjet. And so we would be kind of on this curve coming up to the blue line. And so when we finish that, rocket-based combined cycle, we are going to use more propellant to get up to top speed. And so you might do some math and say, I kind of integrate this curve. It looks like 20% to get up to top speed. Okay. So yes, we use more, because if you do the same thing with turbine-based combined cycle, including, right, you have to take care of these kind of thrust pinches and things like that. That this is not just integrating this forward. It's understanding the thrust to weight and the lift to drag of the systems. This would be something like 13%. And again, you might say, hey, that means turbine-based combined cycle wins. Well, hang on. In addition to all the other considerations, let's now add in the weight of the system. Rocket engines are pretty lightweight compared to the thrust they generate. On a standard rocket, it might be only 2% of the weight of the system. They're pretty powerful. They pack a big punch. And so then in rocket-based combined cycle, you have to add in the ramjet, you have to add in the inlet, right? But we have no other moving doors, cocoons, any of this different stuff. And so, let's say maybe this is 5%. So we go from 2 up to 5%. And then turbine-based combined cycle, so jet engines are normally about 10% of the weight of the system. And so then you're going to add in kind of the same sort of systems, but they have more doors and things like that. So I'm not going to add 3% to that system. I'm going to add 5% because of all the extra things that that jet engine turbine-based combined cycle has to carry. And so we'll say that is about 15%. And so if you add those two up, you're now saying that this is 28% of the mass of the system, right? Kind of the propellant and the engine to get up to cruise is 28%. And then on the rocket-based combined cycle, this might be something like 25%. And so what does this mean? So some of it, we end up winning a little bit more. Rocket-based combined cycle, will be a little bit less total weight to get up to that system, which means we can convert some of that into extra fuel. And so there will be an extended range that rocket-based combined cycles can get to, in addition to all the other kind of benefits we've talked through. And so that's kind of step one on hypersonic, that we're still looking at the range, right? How far can we go? We're all interested in the long haul flights, right? Crossing an ocean. And you want to take a look at, what does it take to get up to that top speed? How much propulsion to get there? And then, of course, how much can you actually pack into your aircraft? But remember, the definition of hypersonic is, heat is your number one issue. And so as we're kind of comparing these two things, we actually need to now, okay, we've looked at propellant. Now we need to talk about heat in a little bit more detail than we had in the past. And so going into heat, so kind of block this off, we're going to talk about heat now. Talk about heat. And there are really three versions of heat. In that first overview, I was really just talking about skin friction just to give you the idea behind all of this. And so, there's skin friction. And if you remember, we had said that skin friction was roughly, the heat energy was roughly that dynamic pressure. So whatever pounds per square foot, or whatever your dynamic pressure the aircraft is flying at, times the velocity. Now, that gets radiated away at t to the fourth. And so you had remember those intercepts of, hey, what can my temperature handle? So you have that. Now, there's also the leading edge. And so anything, whether it's a nose or a wing, that air that is being compressed, right, there's a hot spot that builds up right at that stagnation point. And so that leading edge heat, we all have to pay attention to it. And in the end, some good formulas to kind of correlate this is square root of density over the radius curvature velocity cubed. So what does this mean? This means blunt objects actually have less heating. So when you look at, say, the Apollo, re-entry, or the the Dragon re-entry, any of these kind of re-entry vehicle that are kind of like really kind of curvy, flat bottom, well, that's why they do it. There's a lot of less heat when it kind of have this big radius curvature coming in. And so the same is true. So blunt edges are going to be good for heat, but really bad for drag. So there's always kind of this fight between the radius curvature between the effective heat and that drag. And so some of the more advances where you come in, yes, there's higher temperature materials. You can also think through like some leading edge cooling systems that may help, help win that battle of drag versus heat on the leading edge systems. And then finally, for anybody using kind of a ramjet system, right? If you're drawing air in, whether you're turbine-based combined cycle or rocket-based combined cycle, we all are transitioning to a ramjet. You have to think about the heat problem inside the engine itself, because that air that's on the inside doesn't have, whatever that hot air is and the hot components that are touching that air, they are internal. They're not able to radiate away to the environment. And so just to give some idea of what those temperatures can be, at Mach 4, when you are compressing air, you're slowing air from Mach 4, and through some shocks, you get some compression, which is right back to the suck squeeze bang blow, important step in the ramjet operation. That Mach 4 temperature might already be 1100 Fahrenheit. Now, this would mean stainless steels are okay. Right? You're not quite to the exotic level as super nickel alloy or anything crazier than that, but that's starting to get hot. And then if you wanted to go all the way to Mach 5 and still slowing that air down to subsonic speeds, this is starting to become 1700 Fahrenheit. So this is where you would have to then switch over to an Inconel or maybe some ceramics or maybe some ceramic coatings. And so if you remember in the overview I talked about scramjets, that's part of what scramjets are trying to then do, is at these higher speeds, you really can't slow down the air, it gets too hot. And so what they're trying to do is, well, don't slow down the air as much. Let's try and combust supersonically. That's the idea behind the scramjet, and it's really trying to solve this problem here. It ends up picking up some other problems because now the airflow is going so fast. You actually have their major problem is then inside of this combustion duct. My air is supersonic and can actually mix the fuel in with the air that's going that fast and combust it in time. So that's kind of one step. Now, a couple more things on aircraft. We've talked about the range. We've talked about then how much fuel to get up to that kind of ramjet cruise operation. We've talked a little bit about the heat. Again, to get away from skin friction heat, you will want to go to a higher altitude. That's the benefit of the rocket-based combined cycle. You can then drive up to higher altitudes. Leading edges, we all have to pay attention to that. That's that fight between drag and heat reduction. And then engine point of view, what actually is your cruise speed, Mach 4 versus Mach 5, can have some consequences to your material choices. So then the question then becomes, well, what speed are you going to go choose? Because ultimately, what I want you to see over here before and take a look at this image. Remember I said this, we were not surprised that the ISP was proportional to 1 over V. Remember we walked through that last time. And so you have a term here that's V times ISP, right? And so I actually want you to see that this term is basically constant. And so really, I could write this as some constant term times L over D, and then the propellant, right? It's really constant to first order. And so when you're thinking about going fast, right, are you, let's say it this way, if I double the flow rate of fuel into my engines, if my engines are twice as thirsty, but I'm going twice as fast, then there's no change in how much fuel I used in that situation, right? And so we actually need to then kind of finish with drawing of lift to drag and how is it changing with Mach number. Because you see lift to drag is important here, lift to drag is important here. I've talked about the drag term based on your choices of leading edges. So really we need to finish with kind of the lift to drag diagram. And so what we're doing based on flow regimes, there's Mach 1, 2, 3, 4, and I'll add Mach 5. Okay, so lift to drag in subsonic aircraft, so this would be 5, say 10, and 15. In most subsonic aircraft, you have little something like this. And so if you're flying in a 737, you're actually trying to, say, be up here, but not go too much further. As you start hitting some transonic, parts of your aircraft are starting to go supersonic, like little portions along your system. So there's kind of a sharp fall off. And then military aircraft who do go through those regimes will actually make some trades. They'll actually have a little bit less, but they'll do something more like this, right? Where, military aircraft, some of them have gone up to like Mach 2, 2.4. So you'll see this kind of as military. And then all of the desire in high-speed flight, right? We're actually all chasing systems somewhere in this regime. Now they all kind of fall off with speed, right? Lift to drag gets lower as you get faster. And so this is sort of the goal of that, supersonic transport, if you will. We want to be in this area over here. And so really the only difference between going fast, again, it's not, your fuel rate isn't really the important one, because if you double your fuel rate but you get there twice as fast, to first order, it's not actually what's happening. To first order, the thing that's actually challenging you is that your lift to drag might go from 15 down to 7. So that's why, you might end up having to use more fuel to go that fast. Now, that's not accounting for yet, though, that your ISP might actually be more efficient, to fly that fast. So just at first order, we're talking those principles. But what people do pay for is time. And so just like over here, the range, you see that the velocity, because this turns out constant, velocity kind of fell out of the range equation, but it doesn't fall out of people's wallets, right? There was absolutely a desire to go fast, right? What would someone pay to get there twice as fast, right? That's why you have kind of the Concorde had value. That's where Boom Supersonics looking to kind of bring back something just a little bit lower speed. But then, kind of the hypersonic higher speed companies like us are asking like, yeah, but all of the studies are also showing that, gosh, at Mach 3, Mach 4, there's something really interesting. People are really looking at that from a value of, can I fly across an ocean, have a meeting and get back? Or can I fly across and not waste my day kind of cramped up in 12 hours? So there was an economic value to flying fast. But if we're talking economics, we really also need to do the full story, right? So there's value in flying fast, but from an operational point of view, right, you have to include things like dispatch, reliability, right? Which is, hey, I have an aircraft, it needs to fly. Is it always breaking? Maybe you've had the experience where you board a plane and they're like, something just broke, and it's pretty rare these days, right? Planes have gotten pretty good, but dispatch reliability is important, right? And related to that one is then maintenance cost. How much is it to cost, and how often do I have to go in and cost, and what are the levels of overhaul needed? Also related to that is how many times is this aircraft going to fly a day, which is turnaround, right? Does it require a quick inspection like you have right now in existing vehicles, or is this long overhaul? And so that's one of the reasons we at Venus are also trying to fly higher. We're not trying to fly with any exotic materials that require some crazy level of inspection, right? Whether you have ceramic or you have some sort of kind of carbon, the layers of inspections and time between flights would drive the economics worse. That's why we're focusing on flying with sort of existing kind of titanium level materials that we have a good handle on how to do quick turnarounds, okay? And then on top of that, you have your fuel. And if you're like us and you're carrying an oxidizer, you have those costs. And then you have the total cost of the aircraft amortized around, right? So total, I'll just say it's the aircraft cost. And so these are all of the things then from a hypersonic point of view you need to compare with. So when we're looking at hypersonic, there are some physics challenges, right? They're how far are you trying to go? Can you get that far based on your performance, based on your lift drag, based on how much you're actually able to pack into the vehicle? Right, I mentioned rockets pack 90% of propellant into a vehicle. You can't do that at an aircraft level. 50% is very doable. 70% starts becoming heroic at an aircraft level. You have to take account of how much propellant it takes to get up to top speed, right? Which is kind of your thrust to weight and your lift and drag. That's thrust pinch of your turbine-based combined cycle. Rocket-based combined cycle, we don't have those thrust pinches. In fact, we can accelerate faster. And that's why even though we have lower ISP, the penalty for us to get to cruise is only about 7% different than say a turbine-based combined cycle, with some kind of fuzzy estimations on both sides here, right? But then, of course, the mass of a rocket-based combined cycle should be significantly less than a mass. You're not carrying a big turbine as well. So these kind of flush out in some ways, giving an edge towards rocket-based combined cycle. And then because, again, hypersonic is defined by heat, we looked at heat, skin, leading edge, which we all have to deal with, competing with drag, and then the temperatures of your engine, and then comparing it also now into the economics. And so you actually may end up seeing that, maybe the best economic point of view engineering decisions, maybe it's actually Mach 4. Mach 4 might be actually the perfect one. Ramjet operation, you're up and running. Maybe Mach 4 is great. Maybe it's Mach 4.5. Maybe at Mach 5. Right? There's some cost point at which point, maybe you really want to go Mach 5, but maybe the total cost as you're sort of inspecting it here starts really climbing at Mach 5, and what people would be willing to pay Mach 4 versus Mach 5 might not be worth it. So those are all kind of the big deep dives at this level of hypersonics. Clearly, this is just scratching the surface in terms of aerodynamics and heat transfer on those vehicles. And then, kind of buried in all of these turnarounds are lots of inspections and material sensitive things. So that's a high level here. And so on the next episode, I'm going to go through RDREs and kind of complete that, like detonation engines, what are they in detail? And again, how they help out that rocket-based combined cycle become a reality. Thanks.